Dr. Chris Lovejoy studied medicine at Cambridge. He left his career in medicine to undertake the Machine Learning and Computational Statistics Masters at UCL. After working as a machine learning researcher, he has now co-founded a startup called Billions Health. Along the way, he picked up an MBA as well. We spoke about his career path, advice for medics who have an interest in computational work, and the best applications of the most common machine learning algorithms. I've been a big fan of Chris's work over the last few years, and it was really great to have this conversation. I hope you enjoy. Can you describe your career path to where you are now?
Yeah, sure. So I started out by studying medicine at Cambridge University, and after that, then worked as a doctor in London for several years. And from towards the end of medical school, I became increasingly interested in data science, machine learning. Initially, like kind of self projects. I was always into maths. Really enjoyed machine learning. I really enjoyed the maths and the coding, and then naturally there, like machine learning seemed to be an area that I could spend my efforts and would make sense for medicine. So I did various different projects around that, kind of gradually increased my skills and capability there. That then led into me doing a master's degree at UCL. And after that, then becoming a data scientist and working remotely as a data scientist. And then after doing that for a couple of years, I was like, now is around kind of the time I wanted to start a company at this intersection of data science and healthcare. And that's then what I'm now doing and have been doing since around November or so last year.
Okay, fantastic. And that leads very well into what are the overview? Can you overview the aims of your company, Billions Health?
Yeah, so I mean, I think the fundamental aim really is around enabling health data ownership and like the large scale availability of health data for data science and machine learning tasks. So I know that, yeah, from all the kind of stuff I've done in machine learning, I've seen that there's a lot of interesting applications, but really one of the fundamental issues is around data availability and kind of access for the researchers to get to data. Like there's a lot of very interesting, exciting applications that we can do with machine learning. We're seeing some of those being borne out in cases where the data is a bit more easily available, such as medical imaging. But there's a lot more that could be done that's just limited by data. It's siloed in different hospitals. It's not using the same structure in like one hospital versus another. Sometimes it's digitized, sometimes it's not, sometimes it's digitized in different ways. So really that's like the fundamental problem we're trying to solve is how can we make it so this data is available and not just like available in the sense we like aggregate some large data set and then it gets used for like research or pharma or this kind of thing, but actually what I think the best way and like the most ethical way to do it is actually if people own their health data and they own that in some kind of standardized format, then that naturally means that you can get these large data sets because if you have a study proposal and you're able to talk to these people and like say, are you interested in sharing your data for this study? Then it enables that essentially. So the ownership, I think, is an important part of it.
Okay. And how is Billions Health going to go about doing that?
Yeah, so I think to some extent, I can't give you all the specifics right now because we're looking to raise a seed investment round kind of towards the end of this year. And after that, then a lot of the stuff will become more public. So what can I say? Yeah, I mean, basically that's the problem we're trying to solve.
Absolutely fine. Yeah, no. Is establishing ground truths in healthcare data sets one of the greatest challenges facing machine learning in healthcare today?
Yeah, I think that's definitely like a big one of them. Like that's a big problem. So yes, for sure. I mean, I think another one is probably identifying the right kinds of places to use machine learning and fitting it into the clinical workflow in a way that makes sense. Those two are probably two of the biggest challenges, I would say.
Okay, and so we just had making sure that it's implemented in somewhere that it makes sense, and ground truths. So let's just go back to ground truths. How do you think we're going to fix that?
I think for there might be different approaches to different data sets. Yeah, so I can talk about some of the things that have been tried, some of the things people have thought about, and how that might potentially lead into this situation. I mean, obviously, as I mentioned, this is like something we're fundamentally trying to solve. I can't say exactly how we're trying to do it at the moment, but in terms of things, I mean, some hospital systems and countries naturally like integrate their data more between different hospitals and are moving towards this like standardized format for storing data. So for example, India have just relatively recently created this new, they're actually calling it NHS as well, but it's a national health stack is what it stands for in their case.
Okay.
And this has like a standardized way of storing that data on a national scale. So that will then kind of produce in India this more standardized health data for which, and then like, the standardization itself is kind of a big step towards then the ground truth. I mean, you also need to then like create the ground truth, which can vary. Maybe you need experts to like label that data. It's a bit of a manual process. To some extent, you can use AI to augment that labeling. In some cases, the ground truth will naturally be there because there's some kind of diagnosis or associated label within within the healthcare record.
Could just be like an objective number. Which types of data do you think we really struggle with ground truths the most?
That's a good question. So I'll answer it by kind of considering the easiest one. So I mean, the easiest is where there's some kind of like histopathological diagnosis, or some blood test marker where it's like if it is on this level, then that is like the disease.
We don't need to worry about those ones.
Yeah. So then the opposite end of that. I mean, I guess places where the diagnosis itself is perhaps a bit more subjective. So potentially things like mental health. Some of these conditions, there's a degree of more kind of subjectivity there. And potentially conditions where there are like different subtypes, again, which are more challenging. I mean, I think like ultimately, fundamentally, it's probably places where there's heterogeneity, like in opinion of doctors. And I think I even saw, I mean, there's some conditions, I can't remember the specific one in this case, which maybe is not as helpful, but where if you ask, I think it was some kind of like imaging, and if you ask many different doctors for an opinion on it, I think actually endometriosis might be an example of this. It's not as I understand, it's not a pure radiological diagnosis. There's a degree of which like clinicians will interpret the symptoms in kind of alongside the radiological images, and there's quite a lot of like variation on what constitutes like an endometriosis diagnosis, and so that's like naturally tricky, right, to create a ground truth, because you can bring in some experts, they can label a big data set, but actually it's not clear. So
yeah, absolutely. So just tell me a little bit more about what you think are the biggest difficulties in delivering AI and machine learning into healthcare, and how we're going to overcome those in the next sort of 5 to 10 years.
Yes, in terms of the first part, like what it looks like, I mean, ultimately, before you implement anything, you want to like validate that it works. And the kind of gold standard from a research point of view is like typically randomized clinical trials and seeing how comparing the outcomes with and without some kind of algorithm in a certain position along this kind of like clinical decision making pathway. In some cases, those things are easier to do than others, and there are some kind of like quite smart ways people have integrated this kind of like methodology of doing the comparison. And I'm thinking particularly of like AI and colonoscopy and some of the studies there as like examples of good comparisons. But yeah, it ultimately comes down to needing to prove that when you implement the algorithm, there's better outcomes. Like, because you might have an algorithm that does really well, it like makes some kind of classification decision and does that with high accuracy. But the next step is, okay, what's the impact of that clinically? Like, what decision does that then change, or treatment plan, or how does that impact the overall clinical pathway that somebody is going through? And does that then lead to a positive outcome? And I think actually the AI in colonoscopy is an illustrative example, because in AI in colonoscopy, there was a study, I think a while back, maybe like 4 or 5 years ago now, that showed they could pick up polyps better than like human eyes. So if you had an AI running in the background and you had a human doing a colonoscopy, the AI would pick up these like quite typically small flat polyps that humans might miss. So you had a much higher rate of adenoma detection. But actually, that doesn't necessarily mean that there's going to be a better clinical outcome, because hypothetically you might like stop more to like check these adenomatous polyps. Maybe you do nothing about them. Maybe you do, maybe you do something, maybe you don't do something. Maybe they're all benign, right? So actually an algorithm which picks up all these like benign things and maybe gives you a lot of like warnings, like stop here and like, have a look at this one, you'll take a sample, etc., that actually might have like no clinical benefit at all, even though the algorithm is doing something very smart and kind of augmenting human performance along one particular axis. So that's really like the key thing, is going beyond, okay, the algorithm does something, but does that thing then lead to positive clinical output?
Absolutely. Great. And just picking up, going back to Web3. So I had a bit of a Google trying to sort of understand a bit more about it. So yeah, could you just give us a short of Spark Notes, Cliff Notes, summary of what Web3 is and what its benefits are?
Yeah, sure. So in terms of Web3, the name Web3 kind of gives, it puts it in this kind of chain of history, like Web 1, Web 2, Web 3. And what Web 1 is, for context, is like in the early days of the internet, everybody kind of hosted their own websites. It was like quite manual. There wasn't really like a standardized format, and you could like hop around different web pages that people were hosting. Then Web 2 is more towards the like kind of centralized big social media platforms and places where you host most of your content. So, obviously like Facebook, Amazon, Netflix, Google, all these big centralized places where most people will go. So most of the traffic will be to these websites. With Web3, it's kind of returning a little bit to Web 1, and then the whole point about it is decentralization. So rather than all of your data and everything that you're doing on the internet being centrally stored, it actually is stored elsewhere and in a decentralized manner. Potentially, so for example, decentralized social media, as like one example of this, is this movement whereby you would own your like fundamental data, your like social media data, whatever you're creating, and then you can then take that to many different platforms. So right now, like Facebook or Twitter, you can't just like export your Twitter data and go onto Facebook and have that data there. Like they're all kind of very different. Whereas with decentralized social media, you could do that because you have this like fundamental data that is kind of your property, your like object that you own. You can go to a Web3 version of Facebook if you want, and then it has like the newsfeed and the features of Facebook built around this data that you have. And then you can take that data over to Web3 Twitter, for example. I actually don't think it's quite as simple as that, but I think that that's like illustrative in some way around the ways in which this decentralization works out. There's a lot more to it as well. There's the whole like financial aspect, like decentralized finance, and really a lot of stuff within Web3 is kind of centered around new ways of transacting like financial value. I should mention the like fundamental technology here, which is kind of like blockchain, which essentially is just a different way of storing data and reaching consensus on what the state of data is, which can be financial, like who has this amount of money.
Crypto. Yeah.
Versus then also, any other like form of data can also be stored on blockchain.
Okay, fine. And with this sort of decentralized data, so is it stored? So by decentralized, it's not stored centrally; it's stored locally with the person whose data it is. If we're applying that to say healthcare, sort of, I'm guessing these files or these data sets can get quite large. So where does that data go? Does it go into your phone? Does it go into your laptop? Where does that tend to go?
Yeah, so the thing with the decentralized is that normally there'll be like many nodes, is kind of typical terminology, that will store whatever data format it is. So in the case of like crypto, the reason that we know so-and-so has a certain amount of money is because all of the computers in the network, all of the nodes have propagated out the data of like, okay, the current state is that so-and-so just transferred money here, so now this person has more money, and that's like the current state. So then all of these nodes themselves will form a consensus on what the state is right now.
Yeah.
And yeah, it's then it would be kind of a similar sort of principle. It's not isolated. That data doesn't just exist on like one device or wherever. With health data, there's some similarities here. Like ultimately, for like decentralized storage of data, you would have like many nodes that would store that health data. There are some kind of challenges around this with medical data in particular, because one of the things with blockchain is it's like super open. Like I can go and look at the transactions of any wallet and see like what they've sent in and out.
All of them.
It's all public, right? By default. So with healthcare, you don't really want to put healthcare data actually on the blockchain, because then that's going to be public. People can see that and access that. And even if you like encrypted it and like stored it in some way with encryption, that encryption might get broken at some point in the future.
Yeah.
So there is still an open question that, to my knowledge, hasn't really been solved of what is the best way of actually storing and securing healthcare data in a decentralized way. And there are various interesting projects looking at this for specific data types. So for example, like genomes.io are looking at this for genetic data. And yeah, there's other kind of like comparable projects for like wearables derived data and electronic healthcare record data.
Mm.
Um, but it's probably going to involve some type of dividing up of the data. So typically, like one, it might be a large file. You'll divide it up. You'll store those different pieces in different places. You will encrypt that at some level,
Mm.
and the only person who like has the key to then put that all together and unencrypt it would be the like owner of that data, and they can grant permissions to the person that they want to grant permissions to, but it's stored decentrally and not accessible to most people.
I guess my the part of it that I'm still unclear on is just I guess this data storage part. So if the data storage problem can be fixed there, and everyone and this data is sort of chopped up and shared locally, but in a safe way where it's encrypted, and if you have one part of it, it's not it doesn't compromise your healthcare data in general. Is that essentially a short summary of how Web3 with a blockchain works? So you know it's the right person, and everyone would it be that, and everyone would share would store data locally. They might share they might store their own data. Then they'll probably share like the chopped up encrypted version of other people's data. But then it means that you know that it's associated with one person. Does that make sense? Is that sort of an adequate re-explanation of it, or was there anything I missed there?
So I think one thing I probably haven't explained yet is that one of the big benefits of the blockchain side, and this kind of like the fact that it's tamper proof and you can see exactly what's happening,
Yeah.
is that the actual like permission granting and seeing who's accessed that data at what time and whether that's been approved, all this kind of stuff, that will actually be on blockchain as well. So it gives you a
Right.
much higher level of trust. Like if you can imagine right now, some of your health data is probably on a central server somewhere, just on a
Mm.
computer. You have no idea if anyone's like accessed that, and maybe you ask the hospital, they
Yeah.
say, yeah, we haven't showed it to anybody. Fine, but
Yeah.
you're kind of like it's really based on trust. Whereas one of
Mm.
the things with blockchain is like if that data is set up and all of the access management goes via a blockchain, then you can see at what point in time did somebody like
Yeah.
access it, request it, did you
Mm.
give got permission to it, and it makes it kind of like a more trustless way in which you know who's actually accessed that
Yeah.
data essentially.
Fantastic. No,
Um,
it sounds brilliant. I love that. So we'll just move on now to a bit more about sort of medics and developing their machine learning skills. So you had a really good blog post about the importance of projects over, say, taught courses in developing machine learning skills. So my question is, what would you say is the minimum amount of taught course content that you need to learn before starting a healthcare machine learning project? And I'll caveat this question with two things, because obviously this depends on the context of the project or the context of the thing that you're working on. So I would say this is for, say, let's say just data science, analyzing data, standard data science, then doing machine learning, but just applying someone else's model, and then doing machine learning and building your own model. So for each of those three things. Sorry, it's a
so for
horribly
what say those
organized
three again,
question. Yeah.
those three
So
are
standard data science, Python, R, analyzing a large chunk of data and potentially manipulating it however you need to, as it needs to be, and then applying a model, a machine learning model, and building a model.
so the distinction between the first one I said was not clear to me. So the first one is just like analyzing the data and producing kind of output like a graph or like understand the data,
Yeah,
but you're not actually
yeah,
building a model around it. Okay, fine. Okay, that makes sense. Yeah, cool.
yeah.
And then the question was, how much should you know before you do that?
Yeah. Like
Like how many
what
courses?
so you have a fantastic list of like the Andrew Nung
Mhm.
standard machine learning course, etc. So yeah, what would you say is the minimum, the absolute minimum that you need before you go and do each one of those three things?
Yeah, I mean, the kind of like short and maybe slightly trite answer is like just enough courses until you can do them.
Yeah.
That's kind of maybe overly simplistic, but I kind of really see it as like a very iterative process of you're going to material, like building out your understanding, gradually like expanding your capabilities, and then you're trying to do stuff with that. And then when you do the stuff, like you're solidifying the understanding, and you're also opening kind of new questions of, I'm not really too sure like what this kind of space is. And then you kind of dip back into like a course that then covers more of that and gradually expands your knowledge. And it's really just an ever expanding competency circle, let's say.
Mm.
And so in each of those, I mean, for the first data science project, I would say, yeah, just doing like one course on Python for data science, for example. I mean, I think, yeah, like a side note, I think Python, if you're getting started, just makes a lot of sense that like you can't really go wrong if you just learn Python and start learning like pandas and how to do some basic data manipulation and graphs and visualization, all this kind of stuff. So yeah, for the first one, I guess my like more elaborate answer is do like one or two courses, like understand Python, some of the data science libraries that you'll need to use, like NumPy, Pandas, and then just get cracking and try and apply that and analyze the data and see what you learn. In terms of applying someone else's model, a machine learning model, I mean, here, now you should probably understand the machine learning a bit better. So there, probably like machine learning by Andrew Ng, that like kind of foundational course would make sense to do, just to give a bit of the conceptual overview. From a coding point of view, it's not necessarily going to be a lot harder because often if you're applying someone else's model, it is often one line of code to like load that model and then maybe one more line of code to like apply it to the data. So a lot more of it is around the data manipulation and making sure the data is in the right format for the model, which overlaps a bit with the first task of just doing a data science project. The final part of building a model, it really depends on what kind of thing you're doing. If you're not doing deep learning, then this doesn't have to be a lot harder. There's again, sometimes it'll be like a few lines of code, like anything with, so scikit-learn is a popular machine learning package for a lot of these kind of like, let's say more basic algorithms or like non-deep learning algorithms. And again, it's just like import the model, fit model to data, run model and data. It can be very simple. So there, in terms of kind of courses and the amount of things you should do before then, to your question, would be probably like, yeah, maybe some kind of applied machine learning course, something on scikit-learn would make sense. If you're moving into the deep learning side, then I do think it starts to get a little bit more tricky and advanced, and
a bit more
then,
mathsy potentially.
Yeah, potentially more mathsy. I mean, there's a lot of, it really depends how much you're kind of deviating from the script. If you're just importing some kind of model library and applying it, again, you can kind of, often you can get away without really understanding the algorithm deeply and understanding the math deeply. If you are doing anything new, like you're actually kind of coming up with some new model or introducing a variation, then you're going to need to understand all the potential flaws and like pitfalls you can fall into around training, why your weights might not update, and all the sorts of problems that essentially maths understanding is more necessary for. So there, the more innovative you're being, the better like machine learning and maths understanding you'll need. So then you might consider courses like Master and Machine Learning by Imperial College, the Deep Learning Specialization by Andrew Ng again. Yeah, and kind of moving more into that space.
So a lot of healthcare machining work involves data manipulation before applying an ML algorithm on it. And obviously with healthcare data sets, we can get them in any and every form with lots of different types of data. So what can be done to improve that situation?
So I think this again comes back to the standardization of the data that's being used in healthcare, which a lot of this is not easy because it's depending on what sort of electronic healthcare record system you're using, how the data is encoded within that, and therefore like how ready that data is to be used to build machine learning models. So in the kind of perfect world, the solution to this would be having some kind of standardized electronic healthcare record system software that like lots of hospitals use, and clear rules around how they do it.
Or a company that is trying to aggregate everyone's
go.
data. Fantastic.
You're learning very quickly. Yeah.
Absolutely fantastic. Fantastic, Chris. Honestly, fantastic. No, really great. It looks like the questions that I've listed here basically lead inevitably towards the establishment of Billions Health. Right. Anyway. Next question. I sent you an email just before we started with an image of the different types of ML algorithms, and I guess with this podcast, I want it to actually be, trying to really go a bit deeper in the computational side of things. So I've got 9 algorithms. So I will tell you my understanding, and I'm far less technical in machine learning than you, about where each one is useful, and then the ones where I don't have as much knowledge, I'd like you to fill in with where it would be useful. So convolutional neural networks, very good for images. So images, analyzing images. Obviously, neural nets do what they say on the tin. I think that they can be both. So can you? I'm not entirely sure if you do neural nets both supervised and unsupervised. I guess you do just neural nets unsupervised, see if they notice patterns, or supervised, you give them labeled data. Is that a fair assessment of convolutional neural nets?
So yes, I'm trying to think of I know an examples of unsupervised. I think in the majority, if not all cases, you would need to train it in a supervised manner because it would need to have the like labeled outputs that it can then use to update its weights. There might be like some more kind of hybrid approaches of like a semi-supervised learning where
Yeah.
there's a degree of unsupervised, but yeah, for the most case, it'll be supervised.
Mostly supervised. Okay, lovely. Fine. So k-means clustering. I mean, that's usually x and y axis. You can get different coefficients, can't you? So you don't just have x y axis. K-means clustering can you can have variables as many as you need, and just sort of looking at the distance between the data points, and then trying to aggregate them as much as they aggregate them into the minimal part where they're as not far from each other as possible. Is that about right? Anything else to add there?
Yeah, no, so that's basically it. Like, yeah, you're just kind of trying to find a set
Yeah.
number of clusters and you decide how many clusters. So, I mean, with k-means, a particular application of this in medicine is around finding subtypes of diseases. So there's lots of studies where people have looked at, let's say, for example, some kind of liver disease, and you have all these different blood markers and maybe other symptoms, and you're trying to find from within that what are some different ways in which that disease, like you can find novel subtypes of it. And actually, I think I remember I can't remember a specific example actually at the moment, but yeah. So if you can imagine like there's maybe three subtypes of liver disease that we didn't really appreciate before, and you can now discover this new novel subclassification because the algorithm is able to cluster these subtypes in a way that's very hard for like a human to do.
Brilliant, brilliant. Okay, and then we've got logistic regression. So, I mean, I think I remember that from the Andrew Nunn course. Just again, the image was, or the idea on the image was x and y, but you can have multiple coefficients, and basically just a fancy, quite a fancy line that sort of follows it and tries to sort of go one side, the other side, or follows a line and says this is roughly what we would expect for this value, and sort of extrapolating it along that line. Roughly speaking, about right.
Yeah, I think the key thing here is basically it's an approach for classification, which is similar to like naive Bayes, K-nearest neighbors as well.
Yeah.
So those are all things where if you have some kind of classification problem you're trying to solve, where you're trying to say, for example, these
Yeah.
data points are one disease, these are another disease, or these are symptomatic, not like yeah, disease versus no disease, then all of those are like things you could use for that.
Okay, fine. So let's, and then reinforcement learning, that is the one that tends to be a lot more unsupervised. So just giving the algorithm a pattern or a data set and saying, here, pick up some patterns, more or less. So
So
yeah, reinforcement learning, you can make it supervised and unsupervised.
so it's a bit different. I mean, I've usually seen it as a separate classification, neither supervised or
Mm,
unsupervised. The basically the way reinforcement learning works is that there's some action that the algorithm can take. It has a choice of
mm,
actions, and then ultimately it gets either like a reward or a punishment from that, and
mm,
then that then feeds back into the algorithm in the decision making process.
mm,
So it's a little bit different here in that, I mean, in a way, it's supervised learning because it's taking an action and it's getting some feedback and feeding. That's the kind of like basically
mm,
updating the weights you could look at it as. Um, but it's the way that it's used typically is when there's some kind of setting and simulation it can interact with, which is why this is very popular for things like video games, or chess, or like some of these games where there's then some kind of like concrete feedback coming
mm.
back into it, because then there's always like different. It's very hard to have a data set, supervised learning data set that's labeled all the potential outcomes that you might do, and then what the response is, and use that to like update things.
Mm.
Um, so it's easier if there's some kind of setting you can interact with. So any of these computer games, you like, for example, Pong, like the ball is moving, and you can see that
Mm.
change based on the underlying laws of how that game works.
Yeah, yeah.
Um, there was an interesting kind of big paper in intensive care and giving like vasopressors and fluid, which used reinforcement learning. But as I understand, that project took them like many years, and a big part of the challenge for them was actually setting up the algorithm so that it had this like feedback based on real world samples of patients being given this, and then kind of dealing with
Mm,
this kind of incomplete data problem essentially.
sure. And what were their reward parameters in that study?
So if I remember correctly, I think they used basic like death at a certain number of hours. Um, yeah, so it was basically because this was very sick patients in
It's
intensive
pretty
care.
good. It's a pretty good rule. Death
It's a
equals
fairly
minus
it's a
point.
fairly binary outcome. Yeah,
Yeah.
um, I think that was what it was. Yeah.
Yeah. Okay. Fine. Fine. All right. And okay. So Transformers, LSTM. Don't know what LSTM stands for.
Yeah, so LSTM is a long short-term memory, I think is what it is.
Mm, okay.
These are basically a type of like recurrent neural network. So these are
Mm,
very good for what's called tasks using like sequential data,
mm,
which could, and by sequential data, it's basically anything where like the temporal sequence is important. So
mm,
for example, you could potentially use an LSTM for blood test trends over time because
mm.
there's a clear like temporal nature there in the blood tests. Whether you actually would do that, like really depends on the setting. I think, yeah, you might actually not want to use LSTM in practice, but the the type of data is sequential. I mean, so this is yeah, actually, so I can give a concrete example of an LSTM in that. So in my thesis for my master's, I was modeling blood glucose levels, and we used an LSTM to take in probably like 10 to 15 different variables at any moment in time and try and predict what
Mm,
someone's blood glucose level is.
mm.
Uh, and yeah, there's a kind of a clear time sequence of like every time step you have like the state of play, like did they eat a meal, have they exercised, did they sleep,
Yeah.
what were they doing, like what was their smartwatch telling the algorithm that they were doing,
Mm.
and then based on that, what do you think the blood glucose is? So it's this kind of like temporal sequence approach. Talk about transformers. Like transformers are kind of
Yeah. Yeah.
within like natural language processing because LSTMs initially, if I remember correctly, were developed in natural language processing, which is analysis of text in order to understand what's going on, perform various different tasks. Transformers are kind of an extension of this like recurrent neural network architecture, where yeah, essentially they restructure it, and it's actually less about kind of being like a recurrent neural network and more just taking in all of the weights of like all of the input sequence and then giving some kind of output from that. So this is basically transformers are really good for natural language processing. And you may have seen some of the really interesting like generative language models that have been created to yeah, like OpenAI, I think like GPT-2, GPT-3
Mm.
language models and um, various others like BERT is another like popular one that's been used in lots of different ways. And there's a whole host of like natural language processing tasks you can do with that. You can summarize text. You can infer like the truth of a statement based on the text. You can also generate text, so you can like finish a sentence. Um, yeah, lots of different things.
Okay, great. And gradient boosted trees and naive Bayes are two that I've not heard too much about previously.
Yeah, sure. So naive Bayes, the way this works is it's a classifier. It's like a binary classifier. Um, if I remember correctly, so you basically treat all of the input variables as independent predictors of your outcome, and you essentially form like a probabilistic kind of like Bayesian model for each of those, which is um, yeah, I don't know how best to describe like Bayes, but Bayes is like a kind of
Mm,
classic theorem of like probability of A times probability of A given B over probability of uh, A is probability of B. I think
mm.
you might just check that. Um,
Well, but Bayesian theorem tends to be sort of taking into account taking into account
yeah,
previous
yeah,
it takes into account previous experiences with data that's somewhat related to what it's seeing currently ish. Haven't come across too
yeah.
much Bayesian theorem
Yeah,
previously.
exactly. So it's basically like you have a prior and then you're trying to calculate your posterior. Your prior is like what probability do you expect a certain
Mm,
event happening before before you have any like data on that.
yeah.
And then the posterior is like then what do you update that belief to. So it's kind of
Yeah.
often called like a Bayesian net is also called a belief net for that reason.
Okay.
Um,
Fine.
and yeah, here essentially, yeah. So you do kind of you have like this model for all of the different variables, and it's a way of computing it. So you how exactly does it work again? So you basically you calculate the kind of conditional probability for each of those variables, and then you're able to combine those into a model that then generates a prediction when you have new values of all of those variables using Bayes' theorem.
What are the main lessons you took away from your MBA that you are currently using in your role now?
Yeah, good question. I mean, I think a lot of it is just general kind of business understanding of the kind of things you need to think about. Yeah, so I mean, when you have a startup, a lot of the questions you commonly ask yourself are around market sizing, revenue, business models. Yeah, and having done the MBA kind of gave me just a more solid conceptual structure to like make those decisions within and think about those. Yeah, I think that's the main thing. I mean, I don't think there's not like a specific way in which it's been a game changer for how I think about things, but it's just now whenever I'm thinking about an idea and like assessing it, I have this kind of conceptual framework to then assess the like business viability of it and think about what the kind of key metrics here are, like okay, what's the total market size, what kind of penetration of that market, what kind of business is this from the point of view of cost of acquiring customers and like how long those customers are going to be with your company and what sort of like, so LTV is like the lifetime value of that customer from a business point of view. So just lots of like useful frameworks, I think, for thinking about these kind of decisions in a business context.
And what are the main benefits you get from using Obsidian?
Yeah, the first one is joy. I just love it. But
what is it?
Obsidian.
Yeah, I mean, I had a Google, and it looks like Notion. I don't know if that's a fair comparison, but it looks like a sort of word repository of some sort.
Yeah, so I mean, I think basically it fits into this because class of like probably kind of personal knowledge management systems and tools for storing knowledge. Within that, like I think the one that is most similar to that people have also heard of is like Rome Research. So people sometimes classify these things. I think I've seen a system with like 3 different classifications, and then you have like Rome and Obsidian and like Logsec is another example of these like bidirectional linked notes. So it's less of this like hierarchical folder-based structure. Then you have like Notion, potentially some others like Notion, and then a third one, which I think maybe Evernote is in that third one, but I can't remember the details of that. But essentially, yeah. So that's like how you would classify it. There's a great video by someone called Nick Milo, who like I really like. I mean, his YouTube channel is called Linking Your Thinking, and he made this video right after the Obsidian mobile app was released that kind of like explained how it is a bit difficult to classify exactly what Obsidian is. It's not just like another note-taking system. There's a lot of things that it enables. There's a lot of like key differences around Obsidian versus the other ones that I think are interesting, and yeah, is one of the reasons I kind of like fall in love with it. To your question, like, what do I get out of it? A lot of things. I mean, fundamentally, I do see it as a tool that just helps me to like think better and better translate my internal mental functions and like ideas I come up with and produce into things that I can then do in the real world. Is like the fundamental thing I would say. So, if you set it up to in a certain way, like for example, I'll jot like a lot of thoughts in there, and then I'll structure it so that then they can like get resurfaced, and I can kind of continually build on these different thoughts. And so then over time, I have like a thesis on how I should do one particular area, or I'm like, if I'm learning one subject, like what's my general like approach and thinking around that. And Bridget, this might sound like super high level and vague. So let me know if this is not super tangible, but it's a bit difficult to like really succinctly explain it.
Yeah.
I was gonna say at some point I'm gonna write like a blog or a video just like about this and really like kind of get quite concrete on exactly how it's helpful. But yeah, those are
it Sounds a little bit to me like David Allen's Getting Things Done, which was a really good book. I don't know if you've read it, but it's called the Productivity Bible. So all of your tasks to do, there are four key bits to doing anything or any project. It's information collect, and if all of the human brain's terrible at remembering the information. So if anything that gets thrown at you, if you have an in tray, and it can be a digital in tray. So for me, it's just a literal in tray in my Apple notes on my phone. But anytime I get anything at all thrown at me, it goes in there. And then once you get it, you then review it. So then you have to do a daily review where you sort of go through it and then look at what it is and then decide what you're going to do about it. Does it need to be acted on now, later? Then put it into your and then once you review it, you then decide on it, and then you decide what you're going to do. Put it into your projects list. So you've got a projects list with everything in it. Feed the cat, buy cat food, or whatever it is, everything across all domains in your life, and then finally action it and do something about it. And your projects list writes what the next step is. Sounds a bit similar to that. I don't know. I haven't heard about Obsidian before, but does it overlap with that at all?
Yeah, so I think that there's been to some extent like a bit of a natural evolution in the kind of like product personal knowledge management space. And there's like David Allen, and then one guy's quite influential, like Tiago Forte, kind of describes himself as like the David Allen, the digital David Allen, and the whole second brain thing. And right. Yeah, like so Obsidian. I mean, I think right now on their homepage, right, like they say something second brain, like the place of your second brain. Yeah. So definitely, I think part of the appeal is this like second brain and augmenting the limitations of your human brain with a digital brain.
A big thanks to Chris for taking his time for the podcast. You can find links to his work in the description. If you enjoyed the podcast, please do leave a review. I hope you enjoyed the episode, and catch you next time.